Hello, everybody. My name is Mohammed Asharif, Professor Emeritus of the University of Japan. And today I'd like to talk about acoustic echo cancelling. First of all, what's acoustic echo cancelling? Uh, this is for teleconference system, every day now we are doing Zoom and this kind of teleconference system. The speaker near and the speaker here talking to the microphone and then go to the speaker to the far side, and then after the reverberation on the uh, acoustically on the wall of the far end room, then return to its microphone and back to uh, this the, to us, and then we listen to our voice. So this is a acoustic echo. We would like mm, to cancel this kind of echo. For instance, if this person talk here and then here it shows that it returned to the microphone and back to this person. So what would like to find is this pass, this acoustic pass is to be estimated by an adaptive filter, and this adaptive filter made by digital filter, adaptive digital filter here in parallel, and then minus to this pass to cancel the echo, and then echo will not go to the far end. That's the aim. And then for this we need to we need to make a adaptive filter with some algorithms in order to find the unknown paths of the acoustic echo path here, and then put the same in parallel to the acoustic path in the adaptive digital filter. Then if we reduct from the echo, then this will not go to the far end. Okay. Usually there are many algorithms for this. Generally is least mean square algorithm, LMS, and there are many other algorithms such as NLMS and other. And I proposed new algorithms also for double talk system, but this is it's out of this discussion because it's much more difficult. Just I'm talking about a simple case. Okay, next, in the next slide, I'll show you the FIR finite impulse response filter uh, with this delay line. Z inverse is the Z minus 1 is the delay line, and the tap coefficient C02, C, for instance, this is multiplier coefficient. This coefficient should estimate the echo pass. We don't know this coefficient, but gradually we will adopt this coefficient by some algorithms. Now, the very simple is least mean square algorithm, and then reduce from the target, and then echo will be reduced. This is the generally FIR filter. Well, we can use IR filter also, infinite impulse response, but the echo pass is very long usually, but for instance, in acoustic signal, the sampling rate is 8 kilohertz or 16 kilohertz. So in this case, after a long reverberation, we have many tap coefficient like this, not only four, but many thousands of tap coefficients. So in this case, the algorithms become very complicated if it wants to talk in real, to compute in the real time. So it's very simple case now. The finite impulse response with the simple LMS algorithms. And then here I'm showing you here, for instance, this is microphone, and this is and here it goes to speaker, and then after reverberation or to the near end wall of the room, return to the microphone, and then go to the far side, and then this person will listen its voice, which is annoying. The pass now here, the parallel pass is H nabla, which is adaptive filter. We would like to adjust this H nabla. This H nabla will be calculated by least mean square. That is, what is the least mean square? Is the gradually we are estimated this H nabla by adaptive filter. I will show you in the next formula maybe. And by using only the data that we have is the input data, which is X, and the error signal, which is En, and for instance, step size and so on. Then gradually, after many adaptation, H nabla will goes to H, and then E will be minimized. This is the, I mean, enclosure microphone system. This is the principle of the conventional echo canceller system. Usually we use the least mean square algorithm, but there are many, as I said, many other algorithms. The model for the acoustic canceller, of course, we measure this acoustic pass by actual system, but for instance, for simulation, we use such a room acoustic impulse response representation, for instance, by a random signal and exponential decay exponentially by something like this. This is the reverberation of the acoustic that after many reflection to the wall, gradually it decreases to about minus 60 decibel. We will not hear about any echo. But generally, for instance, for 250 milliseconds, we need to have the impulse response. And well, there's two example here. Original signal is this.
He broke a new shoelace that day. The coffee stand is too high for the couch. The new girl was fired today at noon. They felt gay when the ship arrived in port.
The colt reared and threw the tall rider. It snowed, rained, and hailed the same morning.
The heart beat strongly and with firm strokes. The pearl was worn in a thin silver ring.
Now I showed the echo after passing a bulk delay of 250 millisecond pass. Just it become like this.
He broke a new shoelace that day. The coffee stand is too high for the couch. The new girl was fired today at noon. They felt gay when the ship arrived in port.
The colt reared and threw the tall rider. It snowed, rained, and hailed.
So for those talking in Persian, I will make this for you.
آزمایش جهت بررسی اثر پژواک بر روی سیگنال صحبت در اتاق تلکنفرانس. پژواک یا اکو که از جواب آکوستیکی اتاق به وجود می‌آید باعث فیدبک سیگنال بلندگو به میکروفون شده و در نتیجه آن کیفیت مکالمه دو طرفه تحقیر می‌گردد.
And after 250 milliseconds of the pass,
آزمایش جهت بررسی اثر پژواک بر روی سیگنال صحبت در اتاق تلکنفرانس. پژواک یا اکو که از جواب آکوستیکی اتاق به وجود می‌آید باعث فیدبک سیگنال بلندگو به میکروفون شده و در نتیجه آن کیفیت مکالمه دو طرفه تحقیر می‌گردد.
okay, next I will introduce you many algorithms. The simple one is least for algorithms, but I have made many other algorithms, for instance, like CLMS correlation LMS and ECLMS and other and frequency domain, which is much more complex, but we reduce the other efficiency. The efficiency will be higher, and then it gets better. So for today, that's all. Thank you very much.